Hey guys, today we're going to talk about construction of different types of functions. So section 4.1 of this dealt with sort of fundamental development of the idea of functions and just some basic definitions therein. But obviously if you have one function, sometimes you'll be tempted, or at least I'm tempted, to understand how to create more interesting functions from the ones that I'm already studying. And so section 4.2 is going to be dealing with the construction of functions. And I have some uh, notes already written down here for you guys to look at, because given some functions, there are some obvious ways we can think of creating new types of functions from the functions that we already have. So for example, if I'm given two functions f and g, both mapping a onto b, where a and b are sets, you can create new functions in a very obvious way. Namely, you can add or subtract them, right? You can multiply them, and you can divide them, provided it makes sense to divide them. And in particular, I mean that provided that the denominator does not vanish. Because you know that if the denominator vanishes, then the universe is in trouble. And I say you can add, subtract, multiply, and divide these, provided that adding them, subtracting them, multiplying them, or dividing them actually means something, right? Like, um, as if these are functions of numbers, producing numbers, then it makes sense to perform these operations. But I'm kind of saying this in kind of a broad sense. But again, it's always a good idea to keep concrete ideas in mind when you're thinking of functions. So it's always easy to think about numbers. But what we'd like to do now is to think of more interesting ways to make functions. And so the first type of interesting development we're going to talk about is the inverse. So let f be a function from a to b. Okay. The inverse of f is the relation from b to a with, and so we denote the inverse of f with f and this little inverse sign. And we're going to use set builder notation to build what it really means. So it's going to be the set of ordered pairs, such that if you reverse the order of those elements in those ordered pairs, you get an element that's in the function, original function. So that's how you define the inverse. And notice we define the inverse as a relation and not a function, because in many cases the inverse of a function is not a function itself. Later on, I think in section 4.4, maybe even 4.3, we'll learn the conditions under which the inverse of a function is indeed a function. But for now, we're going to keep it very general and just say the inverse of the function is a relation from b to a. Okay. Okay, so one couple of things to notice is that f is mapping a to b, and then the inverse relation takes elements from b to a. So you're reversing the order. This is what it means to be the inverse. Okay, so another way that you can combine functions. So let functions f and g be defined as functions with f mapping from sets a to b, and g mapping from set b to c. Okay, then we can form what's called the composite. This is similar to the composite of relations we talked about in class a couple of weeks ago. But the composite of f and g then is the relation from a to c. It's the following relation. It's denoted g little circle f that's said to be equal to, in set builder notation, sets of ordered pairs xz in A cross C, okay, such that there exists a y in B with xy in F and yz in G. Okay, so you can use set builder notation, so you can use the composite of two functions to take an element from the domain of the first function you're using into the codomain of the second function you're using. And the important point is that any image that's mapped in the first function, so wherever the first mapping maps its elements, so in this case B, you have to make sure that that set is a subset, if not the set itself, of the domain of the second function. That's the key point. Okay. So example. We can look at an example here. So let f of x equal, okay, let's use set notation. It's going to be the set of points x, y, such that y equals 2x plus 1. And g of x is going to be the set xy with y equals x squared. Okay. In this case, the inverse of f, again, is the points xy such that yx is in f. And so how is yx being in f defined? Well, it's the set xy such that x equals 2y plus 1. And if we solve for y now, that's going to be the set y. It's going to be a set of ordered pairs xy such that y equals x minus 1 over 2. And you'll notice here, this is actually a situation where the inverse of the function is indeed a function. And this is because f of x is just a line. It's a linear function. And so the inverse is also going to be a linear function. Let's try G inverse now. So G inverse is going to be xy such that yx is in G, right? What does that mean? That means it's the set xy such that x equals y squared. And that's actually the end of that, finding the inverse, because we can't be sure that if you go any further that you can find the correct branch of x. Sorry, the correct branch of y. And what I mean by that is, to solve for y in this case, you'll have to take a square root. At this point, it'll become sort of, there's going to be two branches, and it becomes a little bit more complicated. So this is actually sufficient to say this is the inverse relation of G. And in this case, you'll notice this is not a function. Not a function. Because why? Because you can find, for example, 2 points with the same first coordinate. 4, 2, 4, negative 2 are both in G inverse. Okay. Similarly, you can find composites here. So let's find the composite GOF. So that's going to be the set of points xz, and again, I know you all are maybe comfortable with computing these things out, but just to get really familiar with set builder notation, let's just go through this in detail. This is going to be a subset of R cross R, such that there exists a y in R with xy in F and yz in G. Okay, that equals the sets xz. I'm going to suppress this notation. I'm not going to keep writing that that's an element of R cross R. I just expect you to understand that now, that there exists a y in the real numbers with y equals to 2x plus 1 and z equals y squared. And then that tells me that if I square y, I get z. So, and I know that y is equal to 2x plus 1. So if I square 2x plus 1, I should get z. That tells me that's equal to xz, such that z equals 2x plus 1 squared. Okay? So let's try the other way now. What about fog? Well, that's going to be the set xz in R cross R with such that there exists a y in R with xy in G and yz in F, which is going to be equal to the set of ordered points xz such that what is G again? G is there exists a y in R with z equals x squared. Sorry, again, another mistake. Y equals x squared, rather. And z equals 2y plus 1. And now what does this tell me? This tells me I can plug in x squared for y to get the relation between z and x. So that is the set of points xz such that z equals 2x squared plus 1. Okay? And to note that in general, this example illustrates an important point. In particular, it illustrates that function composition is not commutative. In particular, if you look back at the previous example, g of f, the composition of g with f gave 2x plus 1 squared, but the composition of f with g gave 2x squared plus 1. So in general, they're not equivalent. And this kind of motivates the following theorem. Let A, B, C be sets, and f is a function that takes A to B, and g is a function that takes B to C, right? Then the composition is a function that takes A to C, i.e. Goff is Okay, and you can prove this actually. I'm not going to do it because I want you to think about it, but the proof follows from fact that G, F are both functions. And it's quite easy to show, so I'm going to leave it as an exercise for you guys to think about. Okay? So some notational things. Notational things. You can write things like gof of x as g of f of x. So you know that f of x is being mapped, f is mapping x into some point in the domain of g, and then g takes that number and produces some other number. And so if you're tired of this Goff fog type of notation, you can always just really make it really sort of clear what's being applied first to the arguments on the way inside. So here it's very clear to everyone that x is being first acted upon by f, and then once that computation is done, then g is being applied to f of x. Sometimes when people look at this left-hand side here, they get confused with which one's being applied first. Okay. So another example here. Let h of x be equal to sine x, k of x be equal to x squared plus 6, and L of x be equal to the natural exponential. Then h of k is going to be h of k of x, which is going to be h of x squared plus 6, which is going to be sine of x squared plus 6. KOL is k of L of x, which is k of e to the x, which is e to the x squared plus 6, which is e to the 2x plus 6. And lastly, LOH is L of h of x, which is L of sine of x, which is e to the sine of x. And so as you can see now, we're getting some really interesting functions. Okay, so again, let me make a point here to say that whenever you do function composition, you have to make sure that the image of the first function that you're using, so k in this first example, L in the second example, h in this last example, you have to make sure the image of that function lies in the domain of the function that is being applied next. So for example, consider f of x equals x cubed and g of x equals 1 over x minus 8, right? Then g of f of x equals 1 over x cubed minus 8. Now notice f of 2 equals 8 is defined. But 8 is not in the domain of g. And so g of f of 2 is undefined. because f of 2 is not in domain of G. So that is, you just have to be careful when you're applying functions and evaluating functions out, especially when they're compositions, is you have to make sure that you're still within the domain of the second function you're applying. Very important, can get people in a lot of trouble sometimes. Okay. Next theorem related to compositions is that although a function composition is not commutative or abelian, it is associative. So let A, B, C, and D be sets, and let F take a function A to B, G takes a function from takes B to C, and H is a function that takes C to D. Okay. Then H composed with G composed with F is going to be equal to H composed with G composed with F. So function composition is associative. Now to prove this, again, it's not super interesting proof, but let me just, sometimes these function proofs are kind of boring. But for example, you can use first theorem What I mean by that is this theorem right here. You can use the first theorem to show that domain of these two functions is the same, is actually A. Okay. Now let X be an element of A. Then this version of the function, composing H and G first and then composing with F, is going to be equal to H and G being composed and being applied to f of x, right? Which equals H of G of f of x. And now you just work the composition the other way. And you get the result. And out comes the result. Okay, so again, it's just a game with notation, functional notation, but it's still good. Okay. So this type of notation is often represented in what's called a commutative diagram. The relationship between all these sets and these functions. So you have A, B, C, and D. F takes A to B, and G takes B to C, H takes C to D. G composed with F takes A to C, and H composed with G takes B to D. And so you can see the relationship between all these all these functions here. Yeah, this is a common type of tool that's drawn a lot even in linear algebra, or even many algebraists when they get into sort of deep theory about these types of things. It's often first step they take is to draw a commutative diagram. Just something to sort of keep your head organized, and sort of a bookkeeping step to make sure you're not getting lost in the notation. Some other theorems. So let f be a function from a to b, then f composed with the identity function of a is equal to f, and the identity function of b composed with f is just equal to f, right? This is pretty easy to see, so recall the identity functions are these things. They just spit out whatever you put in to them. And so clearly, if you combine the identity map with a function, you're just going to get the function itself. That's what this theorem says. Okay. Next theorem. Let f be a function from a to b with the range of f equal to c. If the inverse relation is a function, sorry, I misspoke. If the inverse relation of f is a function, then the composition of the inverse function with the function itself gives you the identity function on A, and then if you reverse the order, you get the identity function, on B. And this proof can be described by simply looking at this type of a commutative diagram. So you have A here, B here, F does this direction, F inverse does this direction, and this commutative diagram plus how F inverse is defined gives you proof of this. And yeah, I think it's good to keep. The book is kind of bad in this regard. It tries to get really into the nitty-gritty details and tries to make really the theory here really perfect. And sometimes, I mean, it might be interesting to look at because it does give you kind of a different perspective of functions and things like this. But other times it just gets annoying. And so I think for many of these theorems, especially for these topics that which you guys are familiar with, it's good to just get sort of high-level pictures of these theorems. Okay. So definition. Sometimes when you deal with the function, you're not interested in how the function acts in the entirety of the domain that it's defined on. Sometimes you're only interested in how the function acts in a subset of that domain. So in that spirit, let f be a function from set A to set B, and let D be a subset of A. Okay. The restriction of f to D is the function f with this little evaluation subscript d, and that's going to be equal to in set builder notation, x and y, ordered pairs x and y, such that y equals f of x and x is an element of d. That is, you're simply taking elements from that subset of A, D, and you're using the same rule F on those elements in D. Conversely, if G and H are functions, and G is a restriction of H, we say H is an extension of G. Okay, so restriction versus extension. Okay, so when would this become important? The best example of an area where I think these ideas of restriction becomes important is in terms of when you're trying to define the inverse of sine function. So recall, sine is a function from R to R, right? And it oscillates, right? So sine looks something, don't take this as perfect, but it's quite close. Right, so here's 1, here's -1, and say this is 0, so at 0 it's at 0, at pi halves it's at pi, so it's at 1, and then at pi it comes back to 0, then does something like that, and it's an odd function, so it does something like this, right? So notice, because I'm gonna sort of go back to your calculus days, this function miserably fails the horizontal line test, right? If I draw horizontal lines, it pretty miserably fails the horizontal line test. And if you recall to your calculus days, what that means is that the inverse of this in general does not exist. However, if you restrict the domain of this function to be from negative pi to pi, then what you get is really a monotonic function, and you can define the inverse function on that domain, on that restricted domain of arcsine, or sine inverse. So a sine inverse of x exists and is defined here. Okay, so that becomes an important point, is that these restrictions are not only to make your life more miserable in terms of things you need to understand, but they do have a very important application, especially in thinking about inverses of functions. And so, yeah. Okay, another theorem. I'm again trying to relate to your high-level ability to think about functions, to just look at these. So let H, G be functions. With the domain of H equal to A, and domain of G equal to be if A and B are disjoint, then H union G is a function with domain of H union G equal to A union B. Moreover, you can actually explicitly write easily how HUG is defined. It's H of X if X is from A, and G of X if X is from B. And now you can see why this disjoint condition here becomes important. And so, for example, you can think of this with a very easy example. So let H of X be X squared and G of X be 6 minus X. And we're going to take restrictions here, actually. Restrict H of X to X is in negative infinity to 2, and G of X to X is in 2 to infinity. Their union, F equals H union G, is an extension of H and G separately, but not of HUG. Sorry. Actually, that's bad. Let me rewrite that. It's an extension of each restriction. But not of H or G. Okay? So because recall the domains of H and G are for the all real numbers, and so we restrict it, then we combine the union, and so F is an extension of those restrictions. And so F of X, let me draw this to the side here so I can draw a picture. So F of X equals X squared for X less than or equal to 2, and 6 minus X for X greater than 2. And so you draw a picture here, 1, 2, so at 2 you get 1, 2, 3, 4, so you're up here, and then you're also up here, but then once you're 3, 4, 5, 6, right? So you get 6 minus X here, and X squared here. Okay. I know this is just, again, an abstraction of what y'all maybe know. Okay, so we're going to finish off this section with some definitions and some computations here. So let F be a function from a set of reals to R whose domain includes an interval I, we say f is increasing on I if and only if for all xy in I, if x is less than y, then f of x is less than f of y. Similarly, f is decreasing on I if and only if for all xy in I, x less than y implies f of x is bigger than f of y. Okay, so let's go back to this nifty picture I drew here. So from negative infinity until 0, this function is decreasing. And then from 0 to 2, increasing. As I screw up here, I'm just gonna get really bad here. And then from 2 to infinity again, you have decreasing again. But let's do some hardcore proofs now. So, example. Prove that f of x equals x squared is increasing on 0, 2. Okay, so we're trying to prove it's increasing. So proof. Let x and y be taken from 0, 2 with x strictly less than y. So we assume x is strictly less than y. Then f of y minus f of x equals y squared minus x squared, which equals y plus x times y minus x. And y plus x is positive, or at least non-negative, but positive. It's positive because y is strictly less than, y is strictly bigger than x, so that must be positive. And same thing for this next term here, because of this assumption right here, that y is strictly greater than x. And so y squared minus x squared is bigger than 0. So f is increasing on 0, 2. Okay, one more example. Let f of x be equal to 2 plus 1 over x. Prove f of x is decreasing for x bigger than 0. So proof, let xy be in 0 to infinity, and assume x is strictly less than y. Okay? Then f of y minus f of x is equal to 2 plus 1 over y minus 2 plus 1 over x, which is equal to 1 over y minus 1 over x. Okay, so 1 over y minus 1 over x, we need to know if this is positive or negative. We know x is strictly less than y, and they're both bigger than 0. So let me erase that. So we know, what do we know? We know x is bigger than y. Sorry, x is strictly less than y, and they're both strictly bigger than 0. Which means I can divide everything by x, and I get 0 is less than 1, which is going to be less than y over x, and I can divide everything by y, which tells me that 0 is less than 1 over y, and that's going to be less than 1 over x, which means 1 over y minus 1 over x is less than 0. So fy minus fx, which we showed from above that that's equal to 1 over y minus 1 over x, is less than 0. So f is decreasing on 0 to infinity. And that's about it for section 4.2. Hope you guys enjoyed it. Hope it was a relatively short lecture. Subscribe, comment, like, whatever the standard YouTube stuff. And I'll see you at the next lecture. Thanks.